So yeah, Ron, tell us a bit about yourself, though, and about the talk that we're going to play in a sec.
Right. So I work at Oracle in the Java Platform group. That's the group that develops OpenJDK, or rather leads the development of OpenJDK. And that's where most of the new features in Java, this is how they're developed. And I am the technical lead for Project Loom, which is a project to add what we now call virtual threads to the JDK. It used to be called fibers. So they're still fibers, but they have a different name now. Reasons that you will see in the talk.
Okay. From me personally, you just appeared out of pretty much nowhere. I don't claim to know the entire Oracle team pretty well. Actually, I don't. But I think the first time I heard of you was when you were project lead of Project Loom, which seems to be kind of like a big thing, right? I mean, Loom is important for the JVM as a whole. So what did you do before that? What did you work on before that?
Yeah, so I joined Oracle about 3 years ago. And before that, I had a startup where I was working on a project, among other things. One of the side projects actually was called Quasar. And Quasar did something that is very similar to Project Loom. And that is why I was hired by Oracle to work in Project Loom.
Oh, yeah, I heard about Quasar. Exactly, because of what you just said, right? I heard somebody's hacking on something over there that does these fiber thingies, but back then, even now, I don't know a whole lot about it, but back then I knew way less. So yeah, I'm looking forward to the talk to learn more about this very topic. And anybody in chat, right, you can just ask your questions right now. Ron will be there to reply to the simple ones. And if you got more complicated stuff, you can still ask, or we can postpone it. I will probably answer it in the Q&A afterwards, so that we don't have to force long, complicated thoughts through the chat window here. So yeah, without further ado, let's check out Ron's talk.
So today we're going to be talking about how to scale concurrent applications on the Java platform and Project Loom. This slide just says that you can't trust anything I say. Right, so first let's talk about the problem we're dealing with, and that is one of concurrency. Concurrency, at least in this context, is the problem of serving multiple independent requests that arrive at your application simultaneously. A web server is a perfect example of such a concurrent application. This kind of concurrency is governed by this law that is called Little's Law. It says that the level of concurrency, or the number of requests you'll be serving simultaneously, is equal to their rate of arrival times the duration it takes to service each one. So for example, if you have 1,000 requests arriving at your application every second, and it takes you 100 milliseconds or 1/10 of a second to service each one, then you need to be serving 100 concurrent requests, 100 requests simultaneously in order to be stable and not to crash. And this level of concurrency is, of course, for your entire application. And then if you know how much concurrency can each of your servers support, then you can know how many servers you can have. But there are a few subtleties here that you need to pay attention to. First is you'll see that the faster it is that you service a request, the less concurrency you need. That is true, but oftentimes we reduce the duration to service a request by adding concurrency. So for example, suppose that all your application does to service a request is emit requests to 3 microservices. And it decides to do this at the same time, so that, supposing they will run at the same rate, that the service time will be 3 times lower. So you make W 3 times lower, but you also multiply your concurrency by 3. So if you want to do back-of-the-envelope calculations, the best thing to do is to consider W to be the time it would take to service the request if you were doing the entire processing sequentially. Right, so in Java, concurrency generally means threads. And threads are a central construct of the Java platform, and much of it is built around them. Exceptions give you context for problems by giving you the stack trace of the current thread. When you step through an application in the debugger, you step through the execution of a thread. When you create a profile in JFR, then the information is grouped by threads. So threads are a central, if not the central, organizing component for a running Java application. Today, in Java, threads are represented by the Java lang thread class, and we only have one implementation of them, and that is a thin wrapper around OS threads. Now, OS threads must support all languages. It doesn't know anything about how they use a stack, for example, and that is why they tend to be to have a high footprint. If it doesn't know how the application uses a stack and how much of it actually needs, it has to allocate a large contiguous stack. Also, switching from one thread to another, something called task switching, has to go through the kernel, which adds some overhead. And also the algorithm itself that decides when to schedule each thread into a processor requires a reasonable compromise between very different usages. So you have some threads doing video processing and others doing transaction serving, right? And you have to schedule all of them. So the easiest thing to do when you write a Java application is when you have an incoming request, you create a thread for it. And then that code is easy to read. It fits well with the language and the libraries and the entire platform. But it is a costly resource, and that importance level of concurrency can be quite low. In fact, it will be much lower than the number of open sockets that your server can support. So, what do we do? If threads are expensive, as usual when we have expensive resources, we pool them. So we create thread pools. One way of using them is to grab a thread from the pool every time an incoming request comes in, hang on to it while serving the request, and return it when the serving of that request is finished. That has some problems. For example, if your task is using, the task is the bit that's processing the request, if that uses thread locals, then if it doesn't unset them, the value might leak to the next unrelated task that will reuse the same thread. It also makes cancellation tasks quite complicated, because if some other thread wants to stop the thread that's running your task from running it, it will need to interrupt it. But this is inherently racy, because by the time it interrupts your thread could be running a different unrelated task. And that means that all tasks must be able to deal with spurious interruption. And this makes it more complicated. The biggest problem, though, is that it's not enough. Even if, so this way, instead of creating threads for however many threads are needed for the entire lifetime of the application, we create only however many threads we need at the same time. But even that number could be too low. So in order to make better use of threads in the pool, we need to return them more frequently. So we don't hang on to them until they finish execution, finish running the servicing a particular request, we return them every time they wait on something. On what? They could be waiting on a lock, they could be waiting on a message, they could be waiting on I/O coming in through a channel, through a socket. And this means that all of our I/O operations and all of our synchronization operations require different APIs, right? Because the ones that come with Java hang on to the thread while they're waiting. And those APIs are completely incompatible with the ordinary blocking ones. Also, and perhaps no better than this, is that we lose context. As I mentioned, all context on the Java platform is associated with a thread. Once we break the association between a task, so even during the lifetime of a single task, it is not associated with a single thread. If we get an exception, we don't get the entire context of the task. It is very hard to step through it in the debugger. You go back to the scheduler every time you wait, and it is pretty much impossible to profile well. But it can scale, right? Because then you need only very few threads for very many concurrent tasks. And this kind of programming is called asynchronous. Like I said, it's very scalable, but it suffers from all these problems. In fact, I would say it clashes with the design of the Java platform. And it is also impossible, almost impossible, to take an existing code base and turn into this. You either go all the way or none at all, certainly depending on operations. So developers are faced with a dilemma. They can write simple code that's harmonious with the platform, but can't scale well enough. And when I say can't scale, I mean that the level of concurrency is lower than the level of concurrency that the server can support. And that means that you need to get more hardware unnecessarily. So it actually costs you money. Or they can write asynchronous code and make good use of their resources, but then their code is incompatible and complex and nearly impossible to profile and debug. So it costs them money too, but in development and maintenance. So either one of these is not a great choice. What we would like is to make threads cheap. And in fact, that is the goal of Project Loom. If we can make threads cheap and we can have many of them, and you can write synchronous code, ordinary code that's in harmony with the platform and with the way people are used to write code, but is also scalable. But the question is then how to expose these new lightweight threads to programmers. And that was a task we were given by the Java architects. Every time we add a new feature to the Java platform, there are two opposing concerns. On the one hand, we would like it to be forward compatible. What does that mean? It means that existing code could enjoy the new feature. A good example of this is lambdas, right? So if you had old Java 7 code that you had a method that took a runnable as an argument, then in Java 8, you could pass it a lambda. So that's forward compatibility, and that's very good. On the other hand, if we have a very attractive feature, it's an opportunity to get people to shift to better APIs and correct past mistakes. And in particular, the Thread API is one of the earliest Java APIs. It dates back to Java 1.0, and over the years it accrued a lot of craft that has no place today. So we studied the way people use threads today in Java. So it turns out that some aspects of the API are very commonly used and others not so much. Thread current thread and thread local are pervasive. So if our new thread-like lightweight thread wouldn't support them, then there would be very little existing code that we could run. On the other hand, ever since Java 5, we've encouraged people not to create threads directly and to join them directly, but rather to make use of the Java util concurrent constructs like executor and future. So people don't actually use the other parts of the thread API so much. So even though it has a bit of baggage, it doesn't really bother them. Thirdly, we now have a policy where we allow to gradually deprecate and then even remove methods from existing APIs, and over time we could clean up the thread a bit. And we realize that the thread class itself doesn't add too much in the way of footprint. So it doesn't make things essentially less efficient. So we've decided to expose this new implementation of thread as Java lang thread 2. So now you have two implementation of threads. One of them is a thin wrapper around OS threads, and the other is an implementation in user mode in the Java runtime. Now, the Java runtime is a good place to put this kind of thread management because it knows much more about your application than the kernel does. It knows you're running Java, and it knows how Java manages the stack. So it knows exactly how much it uses, and it could resize the stack so that it's the footprint it takes is very tight around what it actually uses, and it can change over time. Task switching in user mode can be faster, and we can pick specific schedulers to fit the scheduling algorithm to our particular workload. What we pay is we can't block while we are in native code, because in that case we are like the OS where we don't know anything about that language. That's perfectly okay because that is in fact very rare in Java to call into native code, call back into Java, and then try to block. So we want to assign lots of virtual threads, millions of them, and to a small number of processors. We don't have access in user mode directly to processors, so to approximate those, we will multiplex them on top of existing OS threads, which will become their carriers. So the OS threads will carry on their backs a virtual thread when they actually need to run. We had something quite like that when Java first started. So let me explain the evolution of thread implementations in Java. So in very early versions of Java, we had something called, that was before the hotspot virtual machine. We had something called green threads. And green threads were also threads implemented in user mode, but they could only make use of a single kernel thread, and so a single call. Also, they didn't have pluggable schedulers. Today, we have the ordinary platform threads that are just thin wrappers in one-to-one mapping between Java-lang thread and an OS thread. And what Loom adds is another implementation called virtual threads that can multiplex many virtual threads into many, but less, OS threads. So how did we do? So platform threads have about 2 kilobytes of metadata and 1 megabyte of stack. Now it's true, when you allocate that memory, it is virtual memory, so it's not actually taken from physical memory, but once you use a certain portion of the stack, it is committed forever. It can't be returned to the OS, because the OS don't know how much of it you're ever going to need again. And when you share a thread with many tasks, then it's quite likely that some of them will make use of much of it. And the task switching cost is around 1 microsecond to switch from one thread to another on the same CPU core, and sometimes it can be as high as 10 microseconds. With virtual threads, every thread requires only a couple of hundred bytes of metadata. The stack grows and shrinks over time, however much that particular task needs. And switching from one virtual thread to another is around 200 nanoseconds, although that is heavily dependent on the scheduler you use. So with this, you can have millions of virtual threads. How do we create them? We've added a constructor, start virtual thread, but to make this more configurable, we have a new builder. You can build an unstarted virtual thread. You can build a started virtual thread. You can pass in a scheduler you want to use here, and you can use a builder to create a factory for virtual threads. So all we did was just add another, more scalable implementation of threads. So it doesn't seem like much, but that alone has a huge consequence, because it means that everything we did to avoid the problem of threads being costly, we don't need to do anymore. So, of course, we don't need to return threads to the pool whenever they need to wait for something. We can hang on to them. But more than that, we don't need to pull them at all. We can have millions and just create a new thread, which is very quick operation for every new task. So we can directly represent an application unit of concurrency, like the request, as a thread unit of concurrency, and even break it down further. So if in the process of servicing a request, we want to emit outgoing requests to other microservices and want to do them concurrently, we just create a new thread for each one. So this small change in implementation has a drastic impact on how we write applications. Other languages like C# and Kotlin have gone a different route. In some cases, they didn't have a choice, but I thought just to explain why we didn't go there. So they have something called syntactic coroutines, which are sort of similar to lightweight threads, but the difference is that they are syntactic. Every piece of code has to be marked, but whether it is an ordinary subroutine or a coroutine, and you can't mix the two freely. And like asynchronous code is viral, so the entire call stack has to be one or the other, or otherwise you're not making good use of resources. Moreover, all your APIs, so if you have I/O, you have to have I/O the subroutine version and I/O the coroutine version. Same for synchronization. And those languages have their entire API duplicated. With threads, it's just use the ordinary threads you use today, and just you can have as many of them as you like. So virtual threads, by virtue of them being very cheap and small, already have a drastic impact on how we write concurrent applications. But maybe we can help writing concurrent applications even more. And because we have more threads, perhaps it's a good idea to give users the ability to herd those new multiple threads together. And we found such a great idea that its name is called structured concurrency. The name was coined by Martin Sustrick, and it was popularized, and this is how we found out about it, by Nathaniel J. Smith, who used it quite successfully in Python. And we've decided to experiment with it and possibly adopt it. The principle of structured concurrency is that whenever the flow of execution splits into simultaneous concurrent executions, the original stream does not continue until it rejoins again. So the idea is that the lifetime of these short-lived threads is clearly apparent from the structure of the code. So just like in structured programming, you can't jump outside of a block with a goto, or at least you shouldn't. The same thing is with structured concurrency. The threads you create, their lifetime should not exceed the block in which they are created. So this is what it looks like in our current Loom prototype. So first we have a thread factory that manufactures virtual threads, and we have added this new method to the Javalang concurrent executors class that creates a new thread using this factory for every, it doesn't pool anything, for every incoming, for every task we submit to it. But the bigger change is that we've made the executor service interface extend auto-closable. So when we exit, so we can use it, create it in a try with the resources block, and when we exit the block, when we hit this closing brace, the compiler will emit a call to close, do a close method on this returned executor. And what that close method will do is it will wait until all tasks have finished executing. So we submit two tasks. They will each run in their own individual threads, because this is the kind of executor we selected. And then they'll run. And when we reach here, we wait for them to terminate. And we know that if once we exit this block, we are guaranteed that none of the threads that were created here are still executing. What does this give us? It gives us several things. So first, you can see the lifetime of threads, but also it allows us, it gives us new tools. So if you work a lot with I/O, you know that managing deadlines, if you have an operation you want to give it a certain timeout, and that can become quite complicated because you have to do it for each and every operation. So here what we can do is to say, for this entire execute a service, we give it a deadline of 30 seconds. And then we submit these two tasks. They spawn two threads, and we wait for them to terminate. If one of them or both have not terminated within 30 seconds, then this will automatically interrupt them and cancel them. But either way, we are guaranteed that we cannot exit this block without while those threads are still running. What about managing results of various threads, which is also very important. So we have different combinators. I'll show just an example of one. So this one is invoke any. You can ask the executor, you give it a list of tasks you want to execute. Each of them will run on its own virtual thread because this is how we created this executor. And invoke any says that we are interested in the result of the first thread that completes normally. So if they all throw exceptions, we will throw an exception. If one of them terminates, at least one of them terminates successfully, we want the result of the first, and then we cancel all the others that are still running. And this is just how we do it. So this gives us the result of the first of these that terminates successfully. We have a similar operation called invoke all that collects the result of all those who complete successfully. Okay, what about thread locals? So virtual threads support thread locals, at least by default. Thread local data is actually not just a thread local class. We have stuff called context class loader, and we have inheritable thread locals. And I mentioned before that those don't play well with thread pools because then the values you assign to them in one task can leak to another task. They are mutable and they are unstructured. Once you set a value, it is in effect indefinitely until you set it to a different one. And because of that, because of their very dynamic nature, some aspects of the management have to be taken up by the garbage collector. They employ weak references, and that, in fact, has a big performance impact on them. So can we do better? So we have this idea. The example here is not actually legal Java today. It requires some change to try with resources. We might do that, maybe not. We'll see. So this scope thing, scope variables, they're a bit similar to thread locals. We have one of type integer, the other of type string, and then we bind them. So we bind S1 to be 1, S2 to be hello, and we call foo. Foo gets a value similarly to how you would get a thread local. And it will return hello 1, and this is what we will print here. But why do we put them in a triangle resources? So their values are in effect similar to structured concurrency, only for the duration of this block. What does it mean? Inside this block, they are immutable. Once bound, I cannot assign them another value, but I can create a nested binding. So let's say I assign them to 1 and hello. I call print line foo, it prints hello 1. And then I create a nested scope. In this case, it's in the same method. Usually it will be somewhere down the call stack, where I assign them to and goodbye and call foo again. Foo will print goodbye 2. So this will print goodbye 2. But once we exit this block, we return back to the binding in this enclosing scope. And this will again print hello 1. Now, because they're structured, they play very nicely with structured concurrency. So if you have, if you create a binding of scope variables in this scope, and you have a scope, a structured concurrency scope that's inside it, then you are guaranteed that all the threads created here will have terminated by the time we exit this block. And that means that whatever value put here, it's safe for those threads to use. Also, it's immutable. So threads can inherit the same scope value, the same binding, without actually copying it, as today is required with inheritable thread locals. And they can share it, right? and do it safely. And this is actually very important because with virtual threads, we imagine that people will employ many more threads and many short-lived ones. And this concept of inheriting implicit scope is actually important, and it's important to do it efficiently. Now, these scope variables are much faster than thread locals. They're almost as fast as ordinary fields, or about as fast. And they require less memory. And again, that's very important because we have many more threads. So you have to multiply all the thread locals used by the number of your threads. We expect scope locals, once they're ready, to supplant many uses of thread local. There are others that use thread locals as an approximation of something like a processor local. So they have some data structure. Usually it's mutable, but it's not thread safe. And they want threads to borrow it, mutate it for something like I/O buffers, and then let other threads use it. But there are multiple ones because they don't want contention. So if I have 10 threads running, I want, at the same time, I want 10 copies of this. It would be a very bad idea to use thread locals with virtual threads for that, because those objects are usually quite big and heavy, and we have a lot of thread locals. But what we really want there is something like a processor local, one of these per processor, and we're working on something that would do more or less that. Okay, so what's our status? Most of the JDK, most of I/O, certainly networking I/O, has been retrofitted to work well with virtual threads. So if you're using today's existing I/O, whether it's old I/O or NIO, and you do a blocking operation and you're running inside a virtual thread, blocking is almost free. We have support in the debugger, and we have support in JFR. So when you use a profiler, you can see virtual threads as ordinary threads. And if your virtual threads are blocked on I/O, you'll see exactly which thread doing what operation is blocked on exactly what kind of I/O. And remember, this blocking is essentially free. You can have as many threads as you like. Don't be afraid. Don't pool them. Don't be afraid to create them, and don't be afraid to block them. Some stuff that still requires further work, DNS lookup, we have to think about it some more. File I/O could be interesting in some operating systems. Thread dumps is something interesting. So today, you can ask the VM to give you a stack trace of all the threads. But if you have 1 million threads, how do you make sense of it? So this is something we need to think about. We also want to have a construct perhaps similar to what Go have for channels, as they are quite nice for communicating multiple, a stream of multiple results among different threads. And that is all I have to say. I will take your questions now. Thank you.
Great. They were back. Hi, Ron.
Hi.
That was that was very interesting. Oh, that's the best question. Is oh wait, I have to switch to my You can see my face now. There's a great question in chat which came up right now. Thanks for the presentation. What is the time plan for Project Loom?
Well, you can't give a time plan. It's going to be probably sooner than many people expect, but one of the reasons is that we don't know. With the current release plan, the way things work is that we work on projects, and then when they're ready, we merge them and ship them in the next available release. Now, how do we know when they're ready? Much of it has to do with feedback we get from people. So if you want to make Loom arrive faster, then use the early access builds and give us feedback. Now, there was a question in the chat, quite interesting, that I wanted to answer, rather two. So one was, it mentioned Spring and existing frameworks that use thread rules and thread locals. How would they migrate? So first of all, thread locals work with virtual threads, so you don't need to do anything. Second, if you're using a thread, you should never pool virtual threads. There's just no need to. In fact, it just makes things harder. So what you would do is that replace your thread pools with one of these new executors that creates a new thread for every task, and you're done. So the API is the same. So the executor or the executor service API is the same. It's just that the virtual thread is not reused. There was another question about parallel stream. I didn't quite understand it, but for the time being, parallel streams and virtual threads are different concepts. Parallel streams is for parallelism. If you have a very large array that you'd like to sort, that's the kind of things you would use a parallel stream for. Virtual threads is for concurrency. It's not when you have one task, but when you have hundreds of thousands of independent tasks arriving at you from the outside. In each of them, you could be using parallel streams, but for the moment, you probably wouldn't want a parallel stream that creates virtual threads. You could do that. There are possible uses. We're still thinking about those.
So just to reiterate that specific difference, right? Because parallelism and concurrency in my head is often means like the same thing, but it doesn't. What you're saying is concurrency means you have different tasks that you want to do at the same time, and parallelism is you have one task and you want to start and finish it, but in between you want to branch out as many threads as possible to split it up, right? Like sorting.
To make it faster, yes.
Yeah, to make it exactly. Yeah, to make. Okay. Yeah, there were a couple more questions, right? People are pretty interested in this. I'm not sure. So Daniel, probably get a better overview of which questions you already answered. So Daniel asked one pretty far up. He said, I compiled the EA Loom and tried it with a rather big and old product. I was surprised to have it run and compile off the box. 2 questions. Oh, that was one about Spring, right?
I'll answer those.
Okay, great. Then Mihaly asked earlier, you said that since Java 5 people are discouraged to use Thread API, but now that gets extended, so people are encouraged to use it again?
No, so what I meant was that people today don't normally create, use the thread constructor and use the thread.join, rather they use the JavaUtil concurrent executor. And you should continue to use that. So continue using the JavaUtil executor, concurrent executor, and but use the new executors. So you will use the one that creates a new thread for each request. I see some other questions. What about thread.sleep and current thread? Those will work normally, right? So virtual threads are Java threads. They're just implemented in the Java runtime rather than by the OS, but they behave exactly the same. So anything you do with platform threads today, you'd be able to do with virtual threads. Somebody else asked about TLA Plus. Yes, TLA Plus is unrelated to this. It is used internally at Oracle, not in Project Loom. It's a full method thing. I hope, I know someone on the JFR team wants to use it, and I hope that the garbage collection team would use it as well eventually. Do virtual threads work much like coroutines in Go? Yes, exactly. Except they are a bit more powerful because in Go you can only use the scheduler that's given to you by the Go runtime. Here in Java you have more flexibility and you can plug in your own scheduler. It is a quite advanced feature, but you could choose to multiplex multiple virtual threads on a single platform thread, for example, like on the UI thread. So you have, you can try to imagine various applications of that, but
yeah, I was thinking about that, right? Like doing several things that then take the effect on the event dispatch thread. That sounds interesting. Never thought about that.
Right. So you have control. You have much more control over the scheduling. You can do it yourself. You can use the default one, in which case it works much like coroutines in Go. But you can also plug your own scheduling algorithm.
So do you think, as you said, like the own scheduling is definitely an advanced feature. I think much of, like specifically in web applications, much of the underlying basic concurrency comes from the server, right? From the app server maybe that you're running. So I guess you hope, and we can assume that once they support, well, you know, multi-release jars, they can even support that from the get-go, maybe. But they will support this, right? That ideally they have a switch where I can just put a config flag, and then they will just give me virtual threads instead of
In fact, threads, right? we have some demos. So many of these servers, like so we tried it with Jetty. They are configurable that you can tell them to use a different executor than the one they use. So if instead of giving them a pool, you would give them this new executor that creates a virtual thread,
neat.
You don't need to change it. So today we use Jetty with virtual threads without changing Jetty. And I've heard of some people who tried to use Spring already with some measure of success. It depends on how much control to give you.
Oh yeah, right. So you said that. Sorry, yeah, for interrupting. You said that the frameworks control, the service control, control how much. Well, the amount of control gives to you decides whether you can already try this easily. There was one question which probably touches on how much virtual threads are like OS threads. The question was, which things am I not allowed to do in a virtual thread? Which I guess means like which behave differently than you would say for normal thread. You always said sleep works and thread locals work.
So the things that could pose a problem, the main one is don't call into native code with JNI that blocks. You can use JNI as much as you like, but if you call into JNI and that blocks, then it will actually block the underlying kernel thread and reduce your level of concurrency. It will still work in terms of the semantics of virtual threads and platform threads is the same. But if you want to enjoy the full scalability of virtual threads, then don't call into native code and block there. And another thing, and that limitation will stay forever. There is also a temporary limitation that if you block while holding a native monitor, so that is anything that has to do with synchronized. So inside a synchronized method or inside a synchronized block, if you block an IO while you're holding onto your Java monitor, it will actually block the underlying kernel thread. We hope to remove that limitation. We will remove that limitation somewhere down the line, but currently this is a limitation. And what will happen then is that you will block the underlying kernel thread. We will have some mechanism that will tell you why that's happening, and you're not enjoying the full scalability. So what you should do, the best thing you can do to prepare for Loom is to replace the places where you use synchronized today to guard around IO. It's okay if you use a synchronized map, but if you use it to do an IO operation inside a synchronized method, replace that with Java util concurrent locks. A CIT question, Doug Lee. Yes, Doug Lee is already working on something similar to channels. The design, you can look, so Doug Lee's running the concurrency interest mailing list. He's posted a few drafts of a design that probably changed, but you can look at them there. Will we have an official API to yield pause a virtual thread? It's the same API as thread, right? So you can pause a thread with thread.sleep, and you can block a thread with Java util concurrent lock support.park. So the same API that works for today's thread will work for virtual thread.
I have a quick question. You showed on your slides something that was akin of basically the when you can launch several threads and then you're waiting for results. You can say, like, I'm waiting for the first result, I'm waiting for all of the results. That reminded me a lot of the Completable Future API, right? Where I have some of the same kind of operators. And when I mentally
which API?
The Completable Future API, where you also shoot off a couple of operations, and then you say, look, I want to get the first result or all of the results. I mean, these things are quite differently, but they solve the same or similar, from the user perspective, similar problems, right? I want to get this task run, and I want to get back a result. So will Completable Futures use this, or will this make the use of Completable Futures? We don't need Completable Futures there anymore, right?
Right. So, okay. So this is a good question. So this actually uses Completable Future. The difference is that Completable Future does several things. It has a rich API to collect results, and you would still use those. But the completable future is a huge class with lots of methods, and most of them have to do with asynchronous composition. So you say, I want to do this, and then I want to do that. That is the part that you won't need to use. You will just synchronously block on the completable future on the get call. And you can just call that because blocking. So today you try to avoid doing that because blocking threads is costly. But with virtual threads, blocking a thread is virtually free. So you would still be able to use completable futures, but you can just block on them and call the get method rather than the 100 different variants of the then apply, then whatever.
Yeah, so completable futures, like when you first look at it, it's so overwhelming because it solves, like there are a couple of diagonal requirements that you just have to combine. Basically, one of them is then, well, I want to do the next thing, but what if the next thing also returns a completable future? So you have the map and flat map thing. Then you have do this on whatever thread, or do this definitely in its own async thread. So you have for many versions, there's also an async variant. And then, of course, the error handling. And I think that's another thing that goes away, right? With this error, I just use the try-catch resource. Try-catch or try with resources that I'm used to.
You just call get, and get will throw an exception if there is a problem. Or use one of those, one of the... You are actually raising something interesting, and that is, because completable future has such a big class today, it's possible that all those methods that you no longer need to use will confuse people. So maybe we might need to introduce, a superclass that has only the relevant methods that you would actually need to use. So those are usability concerns that we'll need to think about. Yeah.
So here's the thing, because I have to go back to the stage now. I would love for this conversation to go on if people have more questions. What we can do is, if you people out there are interested, I'll just go away now and leave Ron here alone. Ron, if you're done, you can just leave the studio or just close the tab or whatever, and the stream will run on. You will just have a green background. Ron will just be gone. I will already be gone. And from my point of view, you can stay here for a while longer because now a break is coming up. So that means we don't need the room in the next couple minutes. So as long as Ron has time, of course, and people are still interested, from my point of view, you can just stick around. I just have to head out.
Yes.
That's okay.
I can stay here another, 7-8 minutes. All right.
Yeah, great.
Thank you, Nikolai. Great to be here.
Thank you very much. Yeah, thank you very much for this interesting talk. See you around. Bye.
You're welcome. Bye-bye. Okay, so let's see some more questions you have. Will Loom make NIO obsolete? No, absolutely not. All the uses of NIO will still work. It's just that you can use their blocking variants instead of their asynchronous variants, if you like. Will completable future have parts of its API deprecated? I doubt it. But like I said, we might introduce a new superclass that's just not as big, that would be as useful. In some ways, it's possible to use a thread as a thread pool of virtual threads. I'm not entirely sure I understand. You never pool virtual threads. You could, it's just there's no point in doing it. Preemptive, what do you say? Preemptive multi-threading is used within the JVM, but cooperative with native code. I don't entirely understand that. It's best to think of virtual threads as preemptive multitasking. It's not cooperative. It depends. You can choose the scheduler. It won't today, unless you choose a scheduler that forcefully preempts you after a certain time slice. It will only preempt you when you make certain calls, like when you wait an IO and a lock. That is still technically called preemptive. The thing is that you don't, the places where you can potentially block are not marked. So the threading style is the same as with today's thread, and it's best not to make assumptions. Will it be possible to explicitly cancel virtual threads? That is a terrific question. So we would like to eventually add a cancellation. So part of the reason interruption today is complicated in Java is precisely because threads are shared. We would like to add a new cancellation API, which is going to be easier. But but we haven't been able to come up with something we like yet. So for the time being, you would still use the interruption mechanism, but it will be easier because you know that one thread runs one task. So you probably won't miss the task you want to cancel because by that time the thread will have moved on to another. So if every thread just executes one task, it makes using interruption easy. Everything that works now will continue working. So keep using that. Over time, we might add stuff to make things easier. Thread group. Thread groups, so the question is it possible to use a thread as a thread group of virtual threads? So let me answer that, and then how I think the question is meant to be asked. So thread groups are probably going away. Thread groups are something that's very, very old. We don't, to be honest, inside the JDK team, we're not 100% certain why they were ever introduced. But I think the question was different. I think the question meant, is it possible to schedule multiple virtual threads onto a single platform thread? And the answer is yes. And the way to do that is that when you create a virtual thread, you can give it a scheduler, or you can create a virtual thread factory and give it a scheduler that one will be used by all virtual threads created by that factory. And a virtual thread scheduler is just an executor, any executor. So if you give it the Java util concurrent executors new single thread executor, I think that's the name, and you use that as your virtual thread scheduler, then all the virtual threads assigned to that scheduler will be running on the same platform thread. Okay, so we use the term virtual thread, wine, lightweight thread, fiber, etc. Okay, so that's another interesting question about naming. We started out with fibers. People thought that fibers were this new... the problem in concurrency is that many people use the same terminology to refer to similar but different things. So, for example, Kotlin uses the word coroutine, but their coroutines are not actually coroutines. They're more similar to fibers. And then you need to start explaining the differences. And Windows has a concept of fibers, which are fibers, but different from ours. And then I found that when I was giving talks, I had to explain, listen, fiber is not really a new thing. It's just like a thread. So you don't need to learn this new concept. If you know how to use threads, you already know how to use fibers. So we realized it just makes things complicated. So we're looking for a different name. So we thought of using lightweight thread. The problem with that is that lightweight is a relative term, right? So it's lightweight compared to today's thread, but maybe in 5 years, we will have something that's even lighter weight. So what we call them? We call them micro threads, etc. So we decided not to use anything that has like a relative thing. So we've been pondering names, and then it was actually Brian Getz who suggested virtual threads, and the connotation it's supposed to evoke is that of virtual memory. So some sort of an unlimited resource that's mapped into some underlying more limited one, and that in one case physical memory, in our case physical threads, which are really operating system threads, and that is the costly resource, but we give the illusion that you can have a lot of virtual memory or a lot of virtual threads by automatically mapping them to physical memory or physical threads. So that's what, and the official terminology is virtual threads. What we don't have a name for is what we call the existing threads that wrap the OS threads. So right now we're experimenting with platform threads. So we'll see how that goes. What sort of feedback are you looking for? Right. So download the early access. The most important kind of feedback is, I've tried to do this with Loom and it was hard. Or I tried to do this with Loom and it worked great. I need to do this. I don't know how to do it with the current mechanisms you have. Or I did this. I expected to have great performance, but performance was worse than I had expected. So so I would say that the best kind of feedback is I've tried to using this for some real world need, and this was my experience. Also, because it's still work in progress, things aren't stable yet, so you will probably get VM crashes. So reporting those and various bugs is also valuable. In which cases will the standard thread or platform thread, I'll try to call them, will still be preferred to virtual threads? I would say that if you have a very long-running computational task, encoding a video, for example, you might want to use a platform thread for that. A good use for virtual threads are threads that serve transactions, and they have the virtual threads are optimized for threads that do a little bit, they wake up or are created, do a little bit of work, and then they wait again, or they terminate. So either they run for a very short time or they run in bursts. So maybe something that reads a message from a queue, a channel, does some processing, sends a result to another channel, and then waits again. So that's the kind of thing that is very well suited to virtual threads. Other kinds of computation are probably better on platform threads. Does Loom address asynchronous execution? So you can forget about asynchronous. Everything with Loom is synchronous, but the performance is the same as asynchronous. Asynchronous, the way you achieve asynchronicity with Loom is create more virtual threads. Suppose you configure your server to create a new virtual thread for every incoming request. And then while serving that request, you need to make 50 outgoing calls, I don't know, 1 to your database and 49 others to microservices. So just inside that incoming request in virtual thread, create 50 more threads. So you'll have, I don't know, 10 million concurrent virtual threads. That's fine. Just create more threads. You decide how many real threads to be used by the executor. Yes, but by default, the number is equal to the number of calls you have if you're using the default scheduler. If you want to decide whether tasks get more real threads this way, I would suggest that the best way to control your level of concurrency is not to decide how many real threads to have in your scheduler. Rather, in your so say you're making calls to your database or to a microservice, let's say a microservice, and you know that microservice can only handle up to 10 concurrent requests. So what I would do is that wrap the call to the microservice with a semaphore, and every virtual thread or every thread, right? It doesn't even matter if it's virtual or not. Trying to make a call to that microservice will grab one of the semaphores, and once they reach 0, the next one will just block and wait. And this way, you can limit concurrency on a much more fine-grained level by resource rather than by, I don't know, groups of threads. So this is actually how we're supposed to write concurrent code. It's just that over the years, because threads were expensive, we sort of gotten used to roundabout ways of doing things. So go back to, you have to unlearn much of the stuff you learned over the recent years and go back to simple stuff like semaphores, message passing, all of that. Can you move a virtual thread to a different thread to continue the execution? Hypothetically, yes. In fact, today, the way it's designed today is that a virtual thread is assigned to a scheduler over the lifetime of its execution, and the scheduler decides which threads run it. By default, yes, every time you resume, you will be running on a different platform thread, but you won't notice it. There is no way for you to know which platform thread is currently running you, unless you call into native code. If you try to ask what is the current thread, you will get the virtual thread.